This video segment is for the three contact connection options that one finds when trying to do finite element analysis in the Catia's FEA workbench. Now, for the people who may be in my CAE class and they're going to be writing a test soon, I repeatedly told you that to ignore these three options. So please do not use them on your midterm. And but if you want to know what it's all about, and for the people who are outside of my class, this video segment may be useful. The situation is this. When we try to do a contact connection, this dialog box opens up, and there are three options here: clearance, friction ratio, and no sliding. And I want to explain these things in the context of very simple example. We don't want to cloud the picture or convolute the picture by taking a complicated situation. So what I'm going to do is I'm going to take two blocks, which are some distance apart. The dimensions are given 1 by 1. This one is 2 inches, and this is 1 by 1, 4 inches, and there is a gap of 1 inch in between them. Now, the bottom of this lower block is fixed, and by fixed, I don't mean clamp. I don't want to clamp it, but I will put it on a roller support. Okay, so this top one is being pushed down until it establishes contact. Okay, establishes contact A, B, C, D, establishes contact with E, F, G, H, and of course it's going to compress this bottom piece. Now, because of symmetry, I need to take only 1/4 of each one of these. So essentially, I'm going to model these two pieces instead of the actual pieces here, and except that there will be roller support on this fictitious size that I have created, and of course there will be one at the bottom because I'm assuming that this thing is not clamped. Okay, so let me go ahead and generate this geometry. It's very simple. Might as well do it together. So we go here. We are in the product. So first we insert the top or the bottom one. Insert a new part in there, and I'm going to call this thing bottom. Right-click properties. This is bottom piece. Bottom. Okay. Let's make it. So I'm going to double click on it, go into part design, and on this bottom plane, I'm going to sketch a 1/2 inch by 1/2 inch square. So 0.5. Okay, and exit, and I'm going to pad it up by 4 inches. Okay, now let me also change the color on this properties on the graphics. I'm going to change the color to grayish. Okay, so then we're going to create the top part. So I'm going to go to product, insert a new part. I'll say no, and I'm going to make it the top. Properties. Product. I'm going to rename this thing to be top. And say OK. Now, the easiest way for me to do this is to create an offset plane from 1 inch from here, and on it draw that rectangle and pad it. So while I'm in this part, let's go to this part, top part, which we are trying to make. I'm going to create a plane, which is 1 inch from that, 1 inch. And then notice that the reason I selected 1 inch because I want to put a 1 inch gap between them. And on this plane, I will sketch that same square, except that it's easier for me to actually project this. Instead of drawing it and making sure it's in the right spot and the right size, projected that face. Okay, and then I'm going to pad it up by 2 inches. So reverse direction, 2 inches. Okay, and I'm going to change the color to yellow. These are, cosmetic. They have nothing to do with our problem, but because the slide looks like that, I did. Now, let's make everything out of steel. So we're going to have apply material. At the assembly level, everything's made out of steel. Metal, steel on that assembly. And we're done here. Okay. So now we're going to go to generative structure analysis. Catia will create 2 meshes for me, one for the top part, one for the bottom one. And I'm not going to change the size of it. I'll leave it the way it is. They are both, I think they're both parabolic, if I'm not mistaken. Yep, parabolic. And these are the sizes. The only thing I'm going to do is to make a local mesh refinement on the bottom of this and the top of that. So, so let me do the local mesh refinement. Although for what we are trying to do, that is, is not a critical issue. But here, you go here in the model manager, right there, model manager. I got this subtool, and this is local mesh. Let me first of all, because there's two parts here, it's asking me which one do you want to do. So let's say the top one, and then it says where. So the support is right here. This is the actually this is the the element that I selected is for the bottom one. So where I want to define is right there, and I use 0.1 there, and do another one this time for the bottom piece, and it says where, and I want there. This is not much different from that, so I'll just leave it the way it is. That's okay. All right. So if you look at your mesh, right-click mesh visualization, it's going to be a little bit finer for both of them at the top and the bottom surfaces. Although here you can't really see it, but there, of course, you can. I mean, as a matter of fact, I may, to be able to see this thing, if you want, I can make this thing even smaller. I'll make it 0.05. 0.05. Okay, and now do it again. Right-click mesh visualization. Or activate this mesh, the same thing. So it's a little bit finer. Oh, I'm sorry. This one was for the bottom block. What I wanted to do actually was to make this 0.05 and activate the mesh. Right, you can see that it's finer here and it's finer. Okay, good. Let us deactivate that mesh. All right. Now, we know that quite a few things are on surface slider because of symmetry, the cut that I made. This is on surface slider, that is on surface slider. Turn it around, so is this, and so is that, and so is the bottom of this bottom block. Okay, good. And then I want to push this top face down by some amount. Notice that the distance here was 1, okay, 1 inch. So first I make it 0 distance. I have to, in Catia, the way it works, first you give it a 0 displacement on that top. 0 displacement in direction Z, because now you can go and change it using the enforced displacement, which is right here. So that restraint that you just put in there, either from the tree or from the screen, you can select the bottom of it, and I'm going to give it a 1/4 of an inch displacement downward. Okay, so this gap, this gap is 1 inch, and I'm going to say, hey, first of all, move that by 0.25 down. Now, obviously, if it does move, it's not going to contact that, but let's actually see what happens when we try to run this, okay? Oh, by the way, one thing I forgot to do, I want to create contact between this face and this face. So first we create a connection between this bottom face, first component, and for the second component, we select that face, and this connection that is just created is a face-to-face contact connection. So here is the face-to-face properties of the face-to-face properties. You see that? Face-face, and contact is right here. So I'm going to select this from the tree or from the screen, and we say OK. Notice that here, when I did this, I just did it. Let me show you once again. On the properties, if you go on the properties, double click on it, notice that these are all unchecked. Later on, we're going to see what is the effect of checking these things. Okay. All right. First thing we do is we're going to say, okay, let's run it. And you'll see a message like this pops up. And it tells you that you can, the connection cannot be created. Okay, and it gives you some comments here, which is not easy to decipher. But what it's saying is really is that there is a. Let me show you again. It's showing that there is a minimum distance. See that the connection is designed to link two closed geometries. Projection tolerance of 0.1, etc., as a result of internal computation. That's fine. So what I'm going to do is that distance seems to be too big. Okay, so what I'm going to do is I'm going to go and bring it down. Although I would have liked to do it with 0.1, which is possible, I'm going to do it 0.2 so that we can see it easier. So let me double click on this plane, double click on this plane. And instead of the distance being 1 inch from that top flat surface, I'm going to make it 0.2. Okay, so I'm going to bring it down. In principle, if we move this thing by 0.25, we move this thing by 0.25, it will actually establish contact in principle. Okay, so let's first of all, let's go back to the analysis, see if it's this time it's running. If we get an error message, then I'm going to come back and reduce it to the tolerance that the first software was suggesting. Let's see now. No, yeah, same thing. So I'm going to change this thing to 0.1. How about that? So I'm going to change this because obviously there's a value that is giving us, and this value depends on the mesh and a few other things. So I'm just going to make it 0.1. Okay, now run it. So when you say push the top down by 0.25, obviously it's going to go through this, and going to go through means establishes contact and should push it down. So let's go ahead and figure it out. Let's go to our generative structure analysis right there and run it. I'm pretty sure this time it's going to go through. Yeah, it's doing the calculation. Don't worry about this warning message. This is a standard warning message. It ran. So let's look at the actually displacement right there. And it's kind of hard to see what's going on. In fact, what I'm going to do is I'm going to change this scale to 1 so that you actually see the exact deformation. It's not scaled up for visual purposes. Let's select the average ISO and change it to material shading. Anything that is bothering you, you can hide. So I'm going to hide all these restraints. And I'm going to hide that thing, that load on the top, which made us push it down. So I'm going to make this thing hide. And these little things, this one, that one. Actually, let me hide this. Okay, and the contact connection is right there. I'm going to hide this one too. And the connection. Okay, there's the situation. And in fact, if you want to see your mesh, see what's going on, you change the rendering to that last one, which is a question mark, and then it shows you the mesh. Okay, so here's the situation. We pushed this part down by 0.25, and there was a gap of 0.1 between them. So actually, it establishes contact and it pushes this guy down, the bottom piece down. And if you look at, in fact, if you look at, there's some stuff here that we don't want to look at. So let me double click on this plot, and on the selection, just show the elements that I want. I don't want these, you know, weird things in between. Those are internal contact elements that are created. Okay, so let's look at the von Mises stress. Okay, notice that, not surprisingly, the stress is pretty much constant throughout this structure. You can see that it's the same color. It should be, okay? Because these are the same material, you know, you're basically the same stress that applies to this is going to be the same stress that applies to that. Now, and in fact, it will match the hand calculation. If you actually went and did this thing by hand calculation, you get pretty identical result. Now, what I'm going to do is I'm going to go back here, and instead of let me go to contact. Let me go to contact. Not here, the property right there. The first thing I'm going to do, I'm going to check the clearance. And for clearance, I'm going to put, how about 0.3. Okay, notice that I checked the clearance. And for clearance, I put 0.3. And then say OK. So it's the same problem. In other words, we are pushing this block down by 0.25. This gap is 0.1. So obviously, it sounds like this should establish contact and go through. So let's run it and find out. Done. Let's check the contact. Look at the values. Look at the values for von Mises stress, 0. So although this was pushed by 0.25 and the gap was 0.1, it should have gone down and penetrated this thing and pushed it down by 0.15 inch, but it didn't. That's because the meaning of this clearance that I put in there is that unless the faces that are declared as being in contact with each other, it moves, unless that top face moves by 0.3, pretend there is no contact. So notice that here, if I come here and make the clearance, for example, let's say I'll make it 0.05. So if I run it now, because this was pushed down by 0.25 and the clearance is much smaller than that, it is going to actually establish contact. So we say, okay, run it. This time it will run. So the physical distance kind of may become irrelevant when clearance is defined and is too big. So let's look at the deflection. Yep, you can see that. Once again, let's go back here. Let's declare the clearance as point, I don't know, let's make it 0.25, okay? So if we make the clearance 0.25, when you push this thing on 0.25, it should establish contact and give us stress values. So let's find out. You should get stress values. Well, because it's really right at the borderline, okay? So so if it's a little bit bigger than 0.25, we're going to get stress value. So let's go back here to contact properties and make this 0.2. How about making it 0.251? So this actually 0.249. That's what I meant. 0.249. Okay. So the clearance is 0.249, and we're pushing this thing down by 0.25, and now we should get non-zero values for stress. Okay, let's run it. We get huge values, of course. Well, huge values in the sense that pushes it down, but so right there, big values. So I want to show you something here in this slide. So when no option is selected, when over here we don't select the clearance value specifier, we don't do that, and we push the top piece down, when it physically reaches the actual physical gap, the end of the physical gap, and it reaches it, it starts pushing this down. But if we specify a clearance by going there, checking this box and putting a number here, when we do that, and this surface moves, as long as the movement is smaller than this delta, no contact is established. Contact is achieved when the movement is actually becomes delta or bigger. Okay, contact is activated once A physically reaches C, where this is the clearance. The moral of the story is that clearance, if you check it and you put a box in it, put a number in it, may override the actual physical distance. Okay? Let's check it one more time. We go back here. We make the clearance, for example, I don't know, 0.4. The clearance is 0.4 means that unless the top surface moves by 0.4 or more, there is no contact that's detected. Because remember, the gap was 0.1, the top piece is moving down by 0.25, and there should be no stresses there. Should be no stresses. Right there, no stresses. Now, 0.25 clearance was the borderline situation. So even when I put 0.25, I got zero stresses. But when I made it a little bit less, people in my class to fool around with this thing for the midterm because we really haven't discussed this thing at all. So this is just for those people who may be curious. Now, as far as the other things are concerned, no sliding. Let me actually do an example. So I go here. Let me actually make the clearance 0. I'm basically not use it. Okay, so I'm not using clearance, but I will use sliding. Okay, no sliding. Okay, so notice that this is going to move down by 0.25. Obviously, it's going to cover the gap and it's going to push this thing. And when I said no sliding, let me explain to you. Once it runs, I'll explain to you what it means. The name suggests what it means. In other words, the two faces get as if they were glued together, and they have a if you look at it, yeah, no sliding. They get stuck, and essentially, when they get stuck, it becomes one piece. Okay, becomes one piece, and that's why the stress is the same everywhere. Okay. Now, what happens if so no sliding means that once the two pieces reach each other, they get glued, tied, or they don't slide on top of each other. Okay, so let's go ahead here, and in that contact, instead of no sliding, I put down there will be a sliding, but there's a coefficient of friction. I use 0.49, sorry, 0.9 right there. And let's see what happens. So let's run it. So there will be friction in between them, and I expect to be here to have some rather complicated stress distribution, non-constant. Every time you use friction, things become messy because it has to do a lot of, although Catia solves linear problem, except for the issue of contact, it has to do a lot of iterations, and this is why it's taking so long. Okay, there. So let's look at the von Mises stress distribution. Just to see what is going on, it's kind of hard to detect it here. I'm going to double click on this. And let me just look at the top piece, for example. You see that? You see this? This is happening because of friction. Okay. Or if you look at the other one, let's look at this piece. Oh, no. Part two. This is the one. And you can see that if you concentrate on it, you have a complicated situation because we have a friction specified there. Anyway, I hope you found this video useful, and good luck. If you're in my class, don't use it for the test, please.